Three celestial envoys, each on a distinct trajectory, yet their paths intertwined with a hidden design. ʻOumuamua, Borisov, and now, 3I Atlas. All originated from the stars, their journeys too purposeful to be accidental, and they departed without pause. They traversed our solar system akin to probes, assessing atmospheres, analyzing chemical compositions, and relaying data to an unseen origin. Three distinct samples, three separate analyses, each skirting past Mars, Venus, and Jupiter, yet pointedly bypassing Earth. It's as if our planet's status was already determined, our data logged, our chemistry assessed, the task already concluded. And 3I Atlas has not only perpetuated this pattern, but perfected it. Stay with us, because tonight, we will connect these cosmic threads. What we will uncover is a startling reality for which we are profoundly unprepared. If these cosmic enigmas have captured your imagination as they have mine, please show your support by hitting that like button and subscribing, ensuring you don't miss any updates as this unfolds in real time. Share in the comments section where you're watching from, what time it is there, and your thoughts on this new revelation. And if you wish to help our community thrive, please share this video on X, Facebook, Reddit, or even within your private group chats. Your engagement is what allows us to continue exploring stories like this. Thank you for your unwavering support. Part 1. The Silent Geometry of 3I Atlas. History is punctuated by moments when the cosmos bestows upon us revelations we are not yet equipped to comprehend. July 1st, 2025, marked such an occasion. A network of telescopes in Chile, part of the Asteroid Terrestrial Impact Last Alert System, detected a movement in the celestial darkness, an anomaly. This entity was christened 3I Atlas, the third object of interstellar origin ever identified, the third visitor from the void beyond our local stellar neighborhood. And as astronomers meticulously charted its course both into the past and future, they uncovered a truth that should send shivers down your spine. Its trajectory is not erratic. It is deliberately precise. Most celestial bodies that venture into our solar system adhere to predictable orbital paths, ellipses gracefully etched by the enduring force of gravity over eons. They orbit, they return, they behave. But 3I Atlas defies this pattern. It does not orbit. Its path is hyperbolic, signifying its origin from an entirely different realm and its return to the galactic expanse. This much we anticipated. What we did not foresee was the route it meticulously selected for its passage. Envision this. An object enters our solar system at an astonishing velocity of approximately 60 kilometers per second, equivalent to about 37 meters every single second. It approaches from the direction of Sagittarius, from the vast interstellar gulf where light itself requires years to traverse the emptiness. As it draws nearer, it begins to navigate our planetary system with surgical exactitude. On October 3, 2025, it passes Mars at a remarkably close distance of 0.19 astronomical units. This is uncomfortably near for an object traveling at such speed. Subsequently, on October 29th or 30th, based on finalized computations, it reaches perihelion, its closest proximity to our Sun, at roughly 1.36 to 1.4 astronomical units. This positions it directly between Earth and Mars. Yet, its journey does not conclude there. On November 3, 2025, it traverses Venus at approximately 65 astronomical units. And then, months later, on March 16, 2026, it sweeps past Jupiter at 0.35 astronomical units. Mars, Venus, Jupiter, three celestial bodies, three specifically chosen worlds. And here lies the unsettling aspect. Earth is conspicuously absent from this itinerary. Consider what these three worlds represent. Mars, the arid planet, the desolate sphere, a realm where water once flowed and life may have begun before its atmosphere dissipated into the void. Venus, the toxic planet, the scorched world, where an unchecked greenhouse effect transformed a potentially habitable planet into a furnace encased in sulfuric acid clouds. And Jupiter, with its retinue of moons, Europa, Ganymede, and Callisto, signifies the worlds of icy oceans, places where liquid water lies concealed beneath frozen crusts, and life might still exist in the darkness. It constitutes a sequence, a progression from arid to toxic to frozen and wet, from past habitability to failed habitability to potential habitability. It is as if an unseen hand traced a line across the evolutionary spectrum of planetary environments, dictating, examine these, measure these, catalog these, and Earth. Earth is to be entirely overlooked. You might be inclined to dismiss this as mere coincidence. Space is vast, and objects traverse it without discernible purpose or design. Random trajectories are precisely that. Random. Occasionally, they align in ways that appear significant to our inherently pattern-seeking human intellect. However, there is more to this phenomenon. The orbit of 3I Atlas is retrograde, meaning it moves in the opposite direction to the majority of objects within our solar system. Furthermore, while its inclination is a mere 5 degrees off the ecliptic, the plane in which most planets orbit, its direction is approximately 175 degrees, placing it in near-perfect opposition to the general flow, yet remarkably aligned with the planetary plane itself. This orientation maximizes its potential to intersect with planetary orbits. Most interstellar objects enter our solar system at arbitrary angles, plunging through it with wild inclinations, bypassing all significant celestial bodies, and then hurtling back into the void. But this object is different. It entered on a flat trajectory, aligned with the plane, passing through the very regions where planets reside. Then there is the matter of its chemical composition. When astronomers directed the James Webb Space Telescope towards 3I Atlas and analyzed the light filtering through its coma, the gaseous and dusty envelope surrounding it, they discovered something peculiar. The coma is predominantly composed of carbon dioxide, not water, nor the typical blend of volatile compounds observed in most comets. The ratio of carbon dioxide to water is approximately 8:1. This is among the highest proportions ever recorded in a cometary body, an inversion of expectations. It is incongruous, or rather sufficiently unusual to warrant a thorough investigation. Carbon dioxide is abundant on Mars and Venus. Mars's tenuous atmosphere consists of 95% CO2. Venus's crushing atmosphere is 96.5% CO2. And here arrives an interstellar traveler, saturated with the very element that defines these two worlds, passing by both in sequence. Had its purpose been related to Earth, one would anticipate the presence of water or organic compounds mirroring our oceans and atmosphere. But it is not here for Earth. It is here for something else. And that, in itself, is cause for considerable disquiet. Scientists continue to classify it as a comet, treating it as a natural celestial body, a fragment of ice and rock that originated around another star billions of years ago and was subsequently ejected into interstellar space due to gravitational interactions. This is the prudent interpretation, the logical conclusion. Yet, when one steps back and considers the geometric precision of its path, the meticulous way it threads through potential habitable zones, and its rich endowment of the very volatile substance that characterizes two of those worlds, a question arises. What if this is not random? What if this route was deliberately chosen? Part 2. Trajectory. A detailed examination from discovery to the planetary waypoints. The discovery itself was almost unremarkable. Atlas, the same system tasked with monitoring potential asteroid threats to Earth, identified a moving dot on July 1st, 2025. Initially, it appeared to be nothing more than cosmic debris. However, as astronomers delved into archival imagery and reviewed earlier observations, they realized this object had been present in the sky for weeks. It had gone undetected. We had all missed it. Once its trajectory was plotted both forward and backward in time, the implications became profoundly apparent. A hyperbolic orbit. That is the technical descriptor for an object not gravitationally bound to our Sun. It originated from beyond our solar system and is now departing. The mathematical evidence is irrefutable. When the orbital energy is calculated and yields a positive value, it signifies an object destined never to return. ʻOumuamua was identified as such. Borisov was also confirmed interstellar. And now, 3I Atlas joins this exclusive cohort of definitively identified interstellar visitors. Its incoming velocity was estimated at approximately 60 kilometers per second relative to the Sun. While fast, it is not an unprecedented speed. This is consistent with an object that has drifted through the galaxy for millions or billions of years, gradually accelerating due to the Milky Way's rotation and the random gravitational influences of passing stars. Its point of origin, somewhere within Sagittarius, does not correspond to any known star system. However, stars are in constant motion. By the time 3I Atlas departed its home system, assuming it ever had one, that star could be situated anywhere in the cosmos. What distinguishes this object is not merely its interstellar nature, but its inclination. 5 degrees off the ecliptic, that is a negligible deviation. Most interstellar objects are expected to enter at random angles, as interstellar space lacks a preferred orientation. One would anticipate a uniform distribution of inclinations across all possibilities. Yet, 3I Atlas is almost perfectly coplanar with the planets. Its retrograde direction, approximately 175 degrees, indicates it is traversing the system within the plane where most planetary activity occurs. Imagine attempting to throw a dart across a room and striking the edge of a spinning disk precisely on its rim. This is the challenge a random interstellar object would face, to remain within the planetary plane. 3I Atlas, however, achieved this feat. Not only did it maintain its position within the plane, but it also timed its arrival to pass 3 significant celestial bodies in succession. Let us meticulously detail these encounters. First, Mars. On or around October 3, 2025, 3I Atlas passes within 0.19 astronomical units of Mars, a distance of approximately 28 million kilometers. In cosmic terms, this is an exceptionally close proximity. Mars possesses a thin atmosphere with a surface pressure of only 6 millibars, yet it is replete with unresolved questions. Methane periodically appears and vanishes. Subsurface ice awaits discovery beneath the regolith. Rovers meticulously traverse ancient riverbeds, and a constellation of spacecraft orbits overhead, diligently observing every phenomenon. These include the Mars Reconnaissance Orbiter, MAVEN, and the European ExoMars Trace Gas Orbiter. As 3I Atlas passes, all these instruments will have an unparalleled vantage point. Next, perihelion, its closest approach to the Sun, occurring at a distance of between 1.36 and 1.4 astronomical units. This places it between Earth's orbit and Mars's orbit. However, Earth itself will not be in its vicinity. We will be at a different position in our annual circuit around the Sun, observing this visitor's maneuver from afar. Following this, Venus. Around November 3, 2025, 3I Atlas passes within 65 astronomical units, a distance of roughly 97 million kilometers. Venus is a world of extreme conditions. Its surface temperatures are high enough to melt lead. The atmospheric pressure is 90 times that of Earth, and its clouds are composed of sulfuric acid. Despite these harsh realities, there is speculation regarding the possibility of life existing within these clouds. Perhaps microbes that could survive in the cooler upper atmosphere, where conditions are almost Earth-like. Japan's Akatsuki orbiter is currently observing, and upcoming missions like Da Vinci and Envision will delve deeper. Through this instrumented corridor, 3I Atlas will glide. Finally, Jupiter, on March 16, 2026, at 0.35 astronomical units, approximately 52 million kilometers. Jupiter, the majestic giant of the planets, possesses a magnetosphere so immense that it would engulf the Sun if it were visible. Within this magnetic embrace orbit its icy moons. Europa, with its subsurface ocean heated by tidal forces, potentially harboring life beneath kilometers of ice. Ganymede, with its own magnetic field and hidden seas. And Callisto, ancient and heavily cratered. NASA's Juno orbiter is currently in orbit. ESA's JUICE mission is en route, and Europa Clipper will soon arrive. The Jovian system is under intense scientific scrutiny, and 3I Atlas will pass directly through it. 3 worlds, 3 distinct stages of habitability, 3 opportunities for an object to sample, to measure, to record. And Earth, the sole planet within this system where life is confirmed, abundant, and unequivocally evident, is entirely omitted from this sequence. One might posit that Earth is too conspicuous, too vibrant, too obvious. Perhaps the entity or entities that dispatched this object, assuming an intentional origin, are already fully aware of Earth. It's conceivable that Earth was catalogued eons ago and requires no further investigation. Or perhaps we are simply not sufficiently compelling. The statistical probability of such a trajectory is exceedingly low. Researchers have estimated these odds, arriving at a figure of less than 0.5% for a random interstellar object to pass this number of significant worlds at such close proximity. 0.5%. While not an impossibility, it is an unsettling figure, one that prompts contemplation on whether one is observing coincidence or deliberate design. This is where the aspect of instrumentation becomes particularly intriguing. All 3 of these worlds, Mars, Venus, and Jupiter, are currently under intensive observation. They are meticulously monitored, with spacecraft either in orbit or en route. When 3I Atlas passes, it is not merely traversing empty space. It is passing through regions where humanity's instruments are actively observing. Cameras, spectrometers, radar, magnetometers. Every tool we have developed to study our neighboring planets will also have the opportunity to study this visitor. But the pertinent question remains: who is observing whom? Part 3. Chemical fingerprint, CO2 dominance and its implications. Comets are essentially time capsules, frozen emissaries from the primordial solar system, or in this instance, from an entirely different star system. Their chemical composition reveals the conditions under which they formed, including temperature, available materials, and radiation exposure. By analyzing the makeup of a comet, one is effectively deciphering a narrative written billions of years ago. And the story 3I Atlas is telling is profoundly peculiar. The James Webb Space Telescope, employing its near-infrared spectrograph, targeted 3I Atlas and captured the light passing through its coma, the halo of sublimating gas and dust surrounding the nucleus. The data returned was unexpected. Carbon dioxide dominated the spectral signature. The ratio of CO2 to H2O was approximately 8:1, meaning 8 parts carbon dioxide for every 1 part water. This is among the highest ratios ever documented in a cometary body. Most comets we examine are relatively rich in water. Water ice is abundant in the outer solar system and within the protoplanetary disks surrounding young stars. Consequently, one would anticipate an interstellar comet to adhere to similar principles. However, 3I Atlas presents a stark contrast. It is, in a sense, arid. Water is present, but it constitutes a minor component. Carbon dioxide is the prevailing element. Other volatile compounds were also detected, including carbon monoxide and carbonyl sulfide, the usual suspects. But the overwhelming dominance of carbon dioxide is the most significant finding. This discovery raises several critical questions. One possible explanation lies in its formation environment. It is conceivable that 3I Atlas coalesced in the outer reaches of its parent protoplanetary disk, far from the central star, where temperatures were sufficiently low for carbon dioxide ice to condense efficiently. Different regions within a disk exhibit distinct chemical compositions. The snow line, the boundary where water ice can form, is merely one such demarcation. There are others for various compounds. A celestial body that formed beyond the CO2 ice line would naturally possess an enrichment of carbon dioxide. Another potential explanation involves the effects of radiation, galactic cosmic rays. High-energy particles pervading interstellar space can alter the chemistry of ices over vast timescales. When these rays interact with carbon monoxide ice, they can transform it into carbon dioxide. If 3I Atlas spent billions of years drifting through the galaxy, subjected to constant bombardment, its surface chemistry could have undergone significant modifications. Recent scientific papers have explored this very possibility. The enrichment we observe might not reflect its original composition, but rather the cumulative result of eons of irradiation. Both of these explanations are plausible and align with natural processes. However, a third possibility exists, one that most scientists are reluctant to entertain, at least in formal scientific publications. What if the chemistry is intentionally designed? Consider this. If one were to engineer a probe for the express purpose of studying planetary atmospheres, particularly those rich in carbon dioxide, one might imbue it with a carbon dioxide signature. This would enable it to blend in, to be perceived as unremarkable. A comet abundant in CO2 passing Mars and Venus, both of which possess carbon dioxide-dominated atmospheres, would not raise immediate suspicion. It would simply appear as another icy body exhibiting typical cometary behavior through sublimation and outgassing. Alternatively, the carbon dioxide might serve a specific function. It could act as a propellant, a tool for atmospheric sampling, or even a deliberate marker, a calling card indicating, "I am here to study worlds characterized by carbon dioxide. Observe me, analyze me." And in doing so, it compels us to reveal ourselves. This, of course, remains speculative. The prevailing scientific consensus is that 3I Atlas is a natural comet with an unusual, yet not impossible composition. Comets exhibit remarkable diversity. We have only conducted close-up studies of a handful, and most of these originated from our own solar system. Who is to definitively state what an interstellar comet should resemble? Each new discovery adds a valuable data point. ʻOumuamua was described as dry, lacking a detectable coma, possibly tumbling and possessing an elongated form. Borisov was icy and active, more akin to the comets we are familiar with. And now, 3I Atlas is characterized by its CO2 richness, representing yet another unique entity. 3 visitors, 3 distinct chemistries, 3 unique fingerprints. If you were designing a planetary survey network, you would deploy different types of probes to investigate diverse environments. You would not utilize the same instrument for every mission. You would customize, vary the payload, and tailor the chemistry to the specific objectives. But we are not yet ready to articulate such a conclusion. To do so would necessitate acknowledging implications for which we are unprepared. It would mean considering the possibility that the galaxy is undergoing a systematic scan. It would lead us to wonder if we are merely a component of someone else's dataset. It would compel us to confront the notion that Earth is not the focal point of any cosmic attention, but rather just one planet among many, quietly being catalogued by an entity we do not comprehend. The chemical signature of 3I Atlas may hold the key. If we can accurately determine its isotopic ratios, measure trace elements, and observe it performing actions that cannot be explained by the simple sublimation of ice, we might find our answer. Until then, we are left with a comet rich in carbon dioxide, traversing past 2 CO2-dominant worlds, and moving through the planetary plane with an almost geometric precision. And that chemistry, that distinctive signature, is situated within the infrared spectrum, precisely where our instruments are most sensitive. It is readily detectable, easily studied, almost as if it is intended to be observed. Part 4. Planetary Corridor Strategy. Why Mars, Venus, and Jupiter? Let us delve into the nature of these worlds themselves. For the more intimately we understand what Mars, Venus, and Jupiter represent, the more deliberate this trajectory begins to appear. Mars, the world that narrowly missed its potential. Approximately 4 billion years ago, Mars harbored liquid water on its surface. Rivers carved valleys, and lakes filled impact craters. A denser atmosphere maintained surface temperatures conducive to the emergence of chemistry, perhaps even life itself. However, Mars is a relatively small planet. Its core cooled, its magnetic field waned. Consequently, without this protective shield, the solar wind gradually stripped away its atmosphere, molecule by molecule, over hundreds of millions of years. Today, Mars is cold, arid, and possesses a tenuous atmosphere. The atmospheric pressure at its surface is less than 1% of Earth's, yet this thin atmosphere is composed of 95% carbon dioxide. And beneath the surface, dust lie ice deposits, subsurface water, remnants of ancient chemistry, the spectral traces of habitability. As 3I Atlas passes Mars at 0.19 astronomical units, it is traversing a world that tells a story of near success, followed by a slow decline. Not a catastrophic failure, but a gradual erosion over eons. Throughout this passage, spacecraft meticulously observe from orbit. The Mars Reconnaissance Orbiter, with its high-resolution imaging capabilities. MAVEN, dedicated to studying atmospheric escape. ExoMars, searching for methane. The Perseverance rover, drilling into rocks that may contain biosignatures. Mars is the most extensively studied planetary body after Earth, teeming with sensors, and 3I Atlas will pass directly through this comprehensive surveillance network. Venus, the world that veered too far. It is remarkably similar to Earth in size and mass, having formed in the same region of the solar system. It likely began with comparable conditions, but something went drastically awry. A runaway greenhouse effect transformed Venus into a hellish environment. Surface temperatures consistently hover around 470 degrees Celsius. The atmospheric pressure is 90 times that of Earth, and its clouds are composed of sulfuric acid. Carbon dioxide constitutes a staggering 96.5% of its atmosphere, making it the most CO2-rich environment in the inner solar system. Paradoxically, despite these extreme conditions, there is speculation about the possibility of life. Not on the surface, but within the upper atmosphere, in the clouds, where temperatures and pressures are more temperate. Microbes could potentially exist suspended in aerosols, deriving sustenance from sulfur compounds and carried by the winds. While this is a long shot, it is not entirely inconceivable. Venus, too, is under intense scientific observation. Japan's Akatsuki orbiter is meticulously charting Venus's atmosphere. Meanwhile, NASA's Da Vinci mission is poised to descend a probe directly through its cloudy layers. The European Space Agency's Envision spacecraft will employ radar to map the planet's surface. Venus, after languishing in neglect for decades, is finally regaining scientific attention. Amidst this renewed focus, the object designated 3I Atlas is traversing the solar system, passing at an impressive distance of 65 astronomical units. Jupiter, the gas giant, isn't the focus itself, but rather the potential it holds. It's a colossal sphere of hydrogen and helium, lacking a solid surface and subjected to immense pressures. However, its moons, Europa, Ganymede, Callisto, and perhaps even Io, are a different story. These are considered icy ocean worlds. Europa's surface bears the marks of extensive cracking and ridge formation, compelling evidence of a subsurface ocean warmed by the gravitational tug of Jupiter. Ganymede boasts its own magnetic field and potentially layered oceans beneath its icy crust. Callisto, though ancient and heavily cratered, might harbor liquid water deep within its interior. These celestial bodies stand out as prime candidates for extraterrestrial life, not on their surfaces, but within their dark, submerged oceans, sustained by the chemical energy emanating from hydrothermal vents. Furthermore, Jupiter's magnetosphere is the largest known structure in our solar system, a vast bubble of charged particles and magnetic fields stretching millions of kilometers into space. Anything passing through this environment encounters intense radiation and complex electromagnetic interactions. For anyone seeking to study a magnetosphere, Jupiter's is the preeminent destination. On the 16th day of March, 2026, 3i Atlas will make a close approach to Jupiter, a mere 0.35 astronomical units away. The Juno spacecraft is already in orbit around the planet, diligently investigating its internal structure and magnetic field. The JUICE mission is en route, specifically engineered to study Jupiter's icy moons. The Europa Clipper will soon arrive, dedicating its mission to Europa. The Jupiter system is about to transform into the most intensely scrutinized region of the solar system, second only to Earth. And 3i Atlas will glide through this celestial theater precisely as all these sophisticated instruments become operational. We see three worlds, representing three distinct developmental stages. Mars, a world that appears defunct. Venus, a world that seems to have failed. And Jupiter, a world potentially teeming with life. This progression, this timeline, depicts an evolutionary sequence of planetary environments, a narrative that offers crucial insights into how habitability can emerge, endure, or ultimately vanish. Imagine being an advanced civilization conducting a comprehensive survey of the cosmos. Where would you dispatch your probes? You'd target worlds that serve as pivotal data points. You'd seek out extreme environments, atmospheres parched and arid, atmospheres oppressively dense, oceans of ice hidden beneath the surface. You'd need to observe the behavior of carbon dioxide across these diverse settings. You'd investigate how magnetospheres interact with different planetary bodies. Your goal would be to understand the full spectrum of possible outcomes, and crucially, you'd likely bypass Earth, the obvious choice, because Earth is already thoroughly understood. Earth is the noisy anomaly, the one broadcasting radio waves and launching rockets into space. Earth stands out as the outlier, the planet where life flourished unchecked and a technological civilization took root. Perhaps Earth was assessed long ago, its data already integrated into your archives. Or perhaps there's simply no need for another assessment. Alternatively, Earth might be deliberately avoided for a different rationale. It's conceivable that whoever or whatever sent these objects, assuming any sentient entity did, wishes to remain undetected. A close pass by Earth would undoubtedly trigger every telescope, every radar system, every deep space tracking station we possess, making international headlines and necessitating a significant response. However, traversing Mars, Venus, and Jupiter presents a far more understated approach, a quiet passage. This offers a corridor for an object to conduct its operations without attracting undue attention. The statistical likelihood of this particular trajectory, less than 0.5%, remains a persistent puzzle. Coincidences do occur, but this instance is exceptionally specific. It's akin to threading three needles in sequence, striking three targets that embody three distinct phases of planetary evolution, all while adhering to the orbital plane where our primary instruments are focused. It could be natural, or perhaps it's engineered. Regardless, we are on the cusp of discovering more, because unlike ʻOumuamua, which we observed departing, 3i Atlas is still with us, actively moving through these designated waypoints. Every telescope we can aim its way is currently observing it. But here's the question that ought to truly concern you. If this is part of a larger pattern, a systematic survey, what transpires when that survey concludes? What happens once the data is collected and transmitted? What occurs when the entity or entities responsible for these objects deem their information gathering complete? Do they return? Do they dispatch something else entirely? Or do they simply update their records and depart, leaving us to ponder whether we were ever even noticed? Part 5. Emerging debate. Is it a natural comet or an engineered object? The scientific community is exercising extreme caution. The moment one suggests an object might be artificial, a line is crossed. You transition from mainstream astronomy to the realm of fringe speculation. From a respected researcher to that individual at conferences, everyone subtly avoids. Therefore, publicly and officially, the prevailing consensus is unambiguous. 3i Atlas is a comet. Admittedly, an unusual one, but a comet nonetheless. The arguments supporting a natural origin are robust. The object exhibits a coma, it's outgassing, jets have been observed, and dust particles surround its nucleus. All of these characteristics align perfectly with the sublimation of ice as the object approaches the Sun, precisely what comets are known to do. Its hyperbolic orbit confirms its interstellar origin, but this does not inherently imply artificiality. Objects are routinely ejected from planetary systems due to gravitational interactions during planetary formation, sending countless bodies hurtling into the void. A fraction of these inevitably drift into other star systems. We have long theorized the existence of interstellar comets, and now we are encountering them. While its chemical composition is peculiar, it's not outside the realm of possibility. As previously discussed, an enrichment of carbon dioxide can occur through formation in frigid regions of a protoplanetary disk or through billions of years of cosmic ray processing. The estimated size, approximately a few kilometers across, falls within the range of known comets. Its rotation, variations in brightness, and spectroscopic signatures can all be attributed to natural processes. Polarimetric studies, which measure how light scatters off dust within the coma, reveal properties consistent with silicate grains and organic compounds, the very materials we expect to find in comets. There is no glaring anomaly, no obvious inconsistency, no definitive proof of artificiality. Yet there are individuals posing questions, not crackpots or conspiracy theorists, but serious researchers with impeccable credentials who are willing to entertain the hypothesis that perhaps, just perhaps, we are observing something more than mere rock. The trajectory is the primary argument. That careful navigation through the planetary corridor, that precise inclination, that sequence of worlds representing stages of habitability. When one crunches the numbers, when the sheer improbability of such a geometric arrangement is calculated, a sense of unease begins to emerge. 0.5% isn't zero, but it's close enough to spark serious contemplation. Then there's the timing. 3I Atlas is passing these worlds during a period when our observational capabilities are at their zenith. We have more spacecraft orbiting Mars than ever before. Missions to Venus are escalating. The Jupiter system is poised to become the most studied location in the solar system. If the objective were to maximize observational coverage and data acquisition, timing a visit for precisely now would be optimal. A coincidence? Likely, but a remarkably convenient one. Avi Loeb, the Harvard astronomer who garnered significant attention for his analysis of ʻOumuamua, has weighed in. He advocates for a thorough examination of interstellar objects for signs of artificial origin, not because he is convinced they are probes, but because the possibility, however slim, exists, and the implications are profound. He argues that even with a 1% chance, we should investigate, gather data, and definitively rule out artificiality rather than dismiss it outright. Other researchers disagree, emphasizing that the burden of proof is exceedingly high. They maintain that extraordinary claims demand extraordinary evidence, and currently the evidence suggesting 3I Atlas is anything other than a comet is, at best, circumstantial. Its unusual trajectory, while peculiar, is not impossible. The carbon dioxide chemistry is explainable. Its passage through the planetary corridor could be attributed to luck. The fundamental challenge lies in the fact that artificial and natural phenomena can appear remarkably similar. If one were to design a probe intended to evade detection, it would likely be made to resemble a comet. It would be equipped with a coma, allowed to outgas, and its chemical composition would be carefully calibrated to match expected natural signatures. The most effective form of camouflage is to conceal oneself in plain sight. And if this scenario is indeed unfolding, if this is a probe ingeniously disguised as a comet, then the only way to ascertain the truth is to get physically closer. This would involve acquiring high-resolution imagery, measuring acceleration that cannot be accounted for by outgassing alone, and detecting a signal, a structure, or a behavior that natural processes cannot explain. However, we are not currently undertaking such measures. Launching a mission to achieve this requires funding, and securing funding necessitates a consensus, which in turn demands compelling evidence. We find ourselves back at the starting point. Consequently, the debate continues, unfolding in academic journals, at conferences, and in hushed conversations between researchers who hesitate to voice their private thoughts publicly due to the immense stakes involved. If 3I Atlas proves to be a natural phenomenon, it represents an invaluable sample of another star system's chemistry, contributing significantly to our understanding of planet formation across the galaxy. If, however, it is artificial, then everything changes. The implications of the artificial hypothesis are simply staggering. It signifies that we are not alone in the universe. It implies the existence of other entities capable of interstellar travel, engaged in conducting surveys and cataloging celestial bodies. It suggests that the galaxy might be populated with autonomous systems, quietly collecting data and transmitting it to an unknown destination. It means we have been observed, measured, and classified. And if we have been classified, into what category have we fallen? Inhabited? Technological? A threat? A resource? Or merely another data point? A footnote in a database so vast that our entire existence is rendered insignificant. The natural hypothesis offers a sense of comfort, preserving the notion of a random universe and our unique standing, or at least sparing us from the implication of constant surveillance. Yet, the artificial hypothesis, however improbable, compels us to confront possibilities for which we are ill-prepared. It forces us to question whether the perceived silence of the galaxy is genuine silence, or if we have simply been looking for the wrong kind of communication. Perhaps the message isn't a radio signal or a laser beacon. Perhaps it is an object traversing space, threading its way through planetary systems, gathering data and moving onward. A silent messenger, a reconnaissance probe, a surveyor. And perhaps we are only now beginning to recognize it for what it truly is. Part 6. The Instrument Hitchhiker. The hypothesis suggests we are inadvertently observing it using our own instruments. Consider this thought experiment. If you were tasked with studying a star system without revealing your presence, how would you proceed? You wouldn't arrive in conspicuous spacecraft or broadcast your existence. Subtlety would be key. You would leverage the system's own infrastructure against itself. In our case, this infrastructure is extensive, providing us with eyes everywhere. Orbiting Mars, the Mars Reconnaissance Orbiter and the ExoMars Trace Gas Orbiter are continuously observing and recording. Venus hosts the Akatsuki Orbiter, with additional missions on the horizon. Jupiter is currently being studied by Juno, with the upcoming JUICE and Europa Clipper missions set to join. On Earth, we have ground-based telescopes, space-based observatories, radar arrays, and deep space tracking networks. We have effectively constructed a sophisticated surveillance system for our own solar system, dedicated to monitoring asteroids, studying planets, and tracking space weather. And now, 3I Atlas is passing directly through the heart of this network. The instrument hitchhiker hypothesis posits that the object is not attempting to evade detection. Rather, it is actively seeking it out. It is deliberately positioning itself precisely where our instruments will detect, study, and analyze it. Because every time we direct a telescope towards 3I Atlas, every time we capture a spectrum or an image, we are not merely observing the object itself. We are simultaneously revealing aspects of ourselves. Reflect on our actions. We are meticulously measuring its composition, precisely tracking its trajectory, thoroughly analyzing its structure, publishing scientific papers, and sharing data globally. All of this information is disseminated, transmitted from observatories, relayed via satellites, and spread across the internet. If the object possesses any capacity for reception, any means of listening, it is effectively learning about us while we believe we are learning about it. This concept is not as far-fetched as it might initially seem. We are aware that celestial bodies can carry instruments. Indeed, we have dispatched numerous such probes ourselves. The Voyager, Pioneer and New Horizons missions are prime examples of human-made probes equipped with sensors, transmitters, and power sources, all designed to observe and transmit data back. An advanced civilization could undoubtedly replicate this feat, perhaps even more efficiently, employing smaller, stealthier systems concealed within what appears to be a natural celestial body. The carbon dioxide coma could serve as a literal smokescreen. When an object outgasses, it generates a cloud of dust and gas that obscures the nucleus, making it impossible to discern fine details or resolve surface features. Anything concealed within this haze, any structure or payload, would remain hidden. The more vigorous the coma's activity, the more effective the concealment. There's another strategic consideration. The object is passing through regions where we have active spacecraft. As it transits Mars, our Mars orbiters will be observing. Upon reaching Jupiter, Juno and the impending missions will have opportunities for observation. However, these spacecraft are primarily designed to study planets, not interstellar visitors. Their focus is directed towards Mars or Jupiter, not passing objects. While retargeting them is feasible, it presents significant challenges, requiring meticulous planning, substantial fuel, and official approval. By the time approval is granted, the object will have already moved on. Thus, the hitchhiker effectively receives a free pass. It navigates through our instrumented zones, is studied by ground-based telescopes that are more readily redirected, and all the while, our most sophisticated spacecraft remain dedicated to their primary missions. This approach is both efficient and elegant, exploiting a vulnerability we may not have previously recognized. But here lies a more profound question. If the object is intentionally designed to be observed, what is the purpose? What is the objective of revealing oneself, even partially? One plausible explanation is announcement. It could be a subtle declaration. We are present, we are observing, and we desire for you to be aware of this. This is not conveyed overtly, but rather through objects that navigate your system with uncanny precision, through chemical signatures that stand out, and through trajectories that provoke contemplation. Another possibility is testing, a method of assessing our response. How swiftly do you detect us? How comprehensively do you analyze our presence? What instruments do you employ? How do you communicate your findings? All of this provides insights into your technological level, your coordination capabilities, and your priorities. Or perhaps the motivation is simpler. It's conceivable that the object must pass through these specific regions for other reasons entirely, such as resource acquisition, conducting measurements, or making course corrections, with being observed merely a secondary consequence. This final option might be the most unsettling. The notion that we are incidental, that our entire endeavor to study this object is simply background noise to its actual mission. The instrument hitchhiker hypothesis also raises questions regarding reciprocity. If the object is observing us as we observe it, what is it learning? What data is it accumulating, and where is that data being transmitted? We do not know, and we cannot ascertain this without significantly closer proximity, utilizing instruments capable of detecting phenomena beyond those characteristic of a natural comet. And herein lies the dilemma. If the object is engineered to appear natural, our established models for cometary behavior will inevitably align. We will perceive what we anticipate seeing, rationalizing away any anomalies. The hitchhiker will then proceed undetected, having fulfilled its mission. This will continue unless we intensify our scrutiny, pose more incisive questions, and become willing to consider the possibility that not everything resembling a comet is, in fact, just a comet. The object's passage through the Martian corridor is already in progress. October 3, 2025 has either passed or is imminent, depending on when this information is being consumed. Did anything extraordinary occur? Did the Mars orbiters detect any unusual phenomena? Did the object deviate from its course? Did it deploy any auxiliary components? We are watching. Data is being collected, and somewhere, someone is meticulously analyzing that data, searching for the anomaly, the signature, the element that defies explanation. Because if the instrument hitchhiker hypothesis holds true, the evidence is undoubtedly present. We simply need to be willing to perceive it. Part 7. The CO2 grazer, a resource harvester concept. Let's explore this concept further. What if the object is not merely observing, but actively collecting resources? The persistent anomaly of enriched carbon dioxide, with a ratio of 8:1 compared to water, is not merely unusual, it's a glaring indicator. And when we consider its trajectory, specifically its planned passage by Mars and Venus, the two inner solar system bodies with the most substantial carbon dioxide reserves, one begins to question whether this chemical composition is coincidental or purposeful. Mars possesses a thin atmosphere, but it's comprised of approximately 95% carbon dioxide, exerting a pressure of about 6 millibars, roughly 6% of Earth's atmospheric pressure, all of which is carbon dioxide. Venus, conversely, presents an extreme, 96.5% carbon dioxide, but at an astonishing 90 Earth atmospheres of pressure. This represents an immense reservoir of carbon dioxide. Venus's atmosphere contains more carbon dioxide than any other body in the inner solar system by several orders of magnitude. And now, 3I Atlas, rich in carbon dioxide, is sequentially passing both these worlds. The resource harvester hypothesis suggests that the object might be actively engaged in collecting carbon dioxide from these atmospheres. While propulsion is one potential application, it's not necessarily the sole purpose. Other uses could include chemical processing, energy storage, or as a raw material feedstock. Carbon dioxide, though a simple molecule, possesses remarkable utility when one understands how to utilize it. It can be broken down into its constituent elements, carbon and oxygen. It can be combined with hydrogen to synthesize methane. It can serve as a working fluid. It can be compressed, frozen, and stored. An advanced probe designed for prolonged missions might require periodic replenishment of resources, not in the sense of propellant, but in the replenishment of consumables. If the probe employs a chemical processing system, if it requires raw materials for repairs or self-replication, or if it stores energy in chemical bonds, then carbon dioxide would be an invaluable commodity, making the targeting of carbon dioxide-rich worlds a logical strategy. The close approach to Mars, at 0.19 astronomical units, places the object well outside the planet's atmosphere. While atmospheric gases cannot be skimmed from such a distance, measurements can be taken, distributions mapped, and any plumes or seasonal variations identified. Furthermore, if the object possesses any form of extended reach or a collection mechanism that extends beyond its nucleus, it could potentially sample the outermost fringes of the Martian exosphere. Venus presents a more intriguing scenario. At 65 astronomical units, approximately 97 million kilometers, the object remains distant from Venus itself. However, Venus possesses a vast atmosphere that extends far into space. Its exosphere, the outermost layer where atmospheric particles escape into space, reaches tens of thousands of kilometers above the surface. Interactions with the solar wind continuously strip away atmospheric material. Evidence of this is seen in the stream of oxygen ions trailing behind Venus, sculpted by the sun's radiation. If the objective were to sample Venus's atmosphere without descending into its crushing depths, it would be accomplished from a distance, by capturing escaping particles and measuring the outflow. And perhaps, just perhaps, a portion of it could be collected for its own purposes. This hypothesis necessitates that the object possesses capabilities beyond simple ice sublimation. It requires active systems, collection mechanisms, and storage capacity. However, if one already entertains the possibility of the object being artificial, then these capabilities are not implausible. We ourselves have designed spacecraft equipped with sample collection systems and have launched missions dedicated to capturing particles and returning them to Earth. An advanced civilization could undoubtedly achieve the same, but without the necessity of a return journey, processing samples in situ, extracting what is needed, and discarding the remainder. The scientific counterargument to this hypothesis is straightforward. Comets sublimate. they do not harvest. The carbon dioxide observed in the coma originates from the nucleus, composed of ice that has remained frozen for billions of years. This gas is released as the celestial body approaches the sun and begins to warm. This is a standard, anticipated phenomenon. There is no need to hypothesize about collection mechanisms. However, the difficulty lies in our inability to differentiate from a distance. If the object is simultaneously undergoing sublimation and collection, meaning it's both expelling carbon dioxide from its ice and gathering it from surrounding planetary environments, our instruments might not definitively distinguish between these two processes. We would observe a carbon dioxide coma, measure the rate of gas expulsion, and calculate the mass loss, all of which would align with existing comet models. The only way to ascertain the truth would be to detect anomalies, deviations in trajectory that cannot be attributed solely to outgassing, or asymmetric jets pointing in inexplicable directions. Variations in composition as the object traverses different celestial bodies, perhaps even a surprising increase in mass instead of a decrease, would also be indicators. Currently, we are not observing any of these phenomena with the required precision. However, if the hypothesis of a resource harvester is accurate, the object's interactions with Venus could provide crucial insights. Venus represents a prime target for resource collection, possessing carbon dioxide in quantities thousands of times greater than Mars. Should the object decelerate, alter its course, or exhibit sudden changes in activity levels that are not correlated with solar heating, it would be significant. This has broader implications. If interstellar probes require refueling and resource acquisition from the systems they visit, they would logically target planets rich in specific resources like carbon dioxide, water, or methane. Their flight paths would be optimized for maximum resource accessibility, appearing purposeful and deliberately designed from an external perspective. This brings us back to the statistical improbability, a probability of less than 0.5%. If the trajectory is designed for resource harvesting, it is not random but optimized, and optimization translates into mathematical improbability. It is important to state that this is speculative. There is no concrete evidence of harvesting, no observed mass gain, and no trajectory anomalies that necessitate extraordinary explanations. Thus far, the object has behaved like a comet. However, our observation campaign is still in its early stages. The Venus flyby has not yet occurred as of late October of the year 2025. Jupiter remains months away, and data collection is ongoing. If the object is indeed harvesting resources, it is doing so with extreme subtlety, precisely as one would expect if the objective is to evade detection. It harvests minimally, maneuvers slightly, and keeps anomalies within the margins of measurement error, operating at the very edge of what is detectable. Advanced technology, after all, does not need to be overt. It can be indistinguishable from natural processes. The most sophisticated technology is often invisible, appearing natural and seamlessly integrated. If entities are dispatching probes across the galaxy to survey planetary systems, they have had billions of years to perfect such camouflage. Consequently, we observe, we measure, and we await anomalies, pondering whether the carbon dioxide emanating from 3I Atlas is merely the frozen residue of another star system, or if some of it originates from our own planets, from atmospheres we are only beginning to comprehend. Regardless, the object is acquiring something from this encounter. Information, if nothing else, which may be all it requires. This brings us to Part 8. The Planetary Defense Reconnaissance Thread. There is an alternative, more strategic and concerning perspective. What if the object's purpose is not sampling or harvesting, but rather a test of our capabilities? Planetary defense is a relatively nascent field. Humanity has only in the last few decades begun to seriously consider the threat posed by asteroid impacts. We have established survey systems like Atlas and Pan-STARRS, cataloged near-Earth objects, and even conducted tests like the Kinetic Impactor experiment in 2022, where a spacecraft was intentionally crashed into an asteroid to assess our ability to alter its trajectory. The DART mission demonstrated this capability, proving that we can, in fact, deflect an asteroid. While our planetary defense capabilities are rudimentary, their very existence implies observability. The deployment of a radar network for asteroid tracking inherently reveals our possession of such technology. Redirecting telescopes to monitor a new object showcases our responsiveness. Publishing analyses of trajectories and compositions demonstrates our scientific coordination. All of this constitutes data. If an advanced civilization sought to evaluate the defensive and technological prowess of a planetary system, they might send an object through it and observe the ensuing response. This is the essence of the reconnaissance hypothesis. The object is a probe, not for scientific analysis, but for intelligence gathering, military or, at the very least, strategic intelligence. It serves as a means to gauge whether the system is passive or active, monitored or oblivious, coordinated or fragmented. The carefully chosen trajectory, navigating the planetary corridor, positions the object precisely within the focus of our sensors. Every telescope tracking it, every spacecraft observing it, every paper analyzing it contributes to a data set detailing our response time, instrument capabilities, observational coordination, and international collaboration, all visible to any observer. Let us examine what the object might have gleaned thus far, assuming it is indeed learning. It was first detected on July 1, 2025, by the Atlas telescope in Chile, not immediately upon entering the solar system, but weeks or even months after crossing its outer reaches. This reveals the limitations of our detection range. We can identify objects once they are relatively close, within a few astronomical units, but we remain blind to the outer solar system, with the exception of the most massive bodies. Following its detection, the object was rapidly catalogued, its orbital parameters determined, and predictions were made, leading to the publication of scientific papers. This entire process unfolded within weeks, demonstrating our capacity for swift analysis, enabling rapid transition from discovery to characterization. However, it also highlights our reactive nature. We did not anticipate its arrival until it was already upon us. Observations intensified, with ground-based telescopes worldwide initiating tracking. Space-based observatories, including the James Webb Space Telescope, were retargeted. Spectroscopic analysis commenced, measuring the object's composition, velocity, and trajectory, all of which were openly shared. This indicates our data-sharing practices and collaborative efforts, but also our lack of secrecy. Any entity with access to our communications would possess the same knowledge. The situation becomes more complex as the object approaches Mars, Venus, and Jupiter. Our spacecraft in these regions present opportunities for observation. However, retargeting a spacecraft is a difficult endeavor, demanding fuel, mission plan revisions, and approvals from mission control, funding agencies, and international partners. This process is inherently slow, bureaucratic, and by the time a decision is reached, the optimal observation window may have closed. A reconnaissance probe would note these institutional inefficiencies. Slow decision-making, divided authority, and spacecraft designed for specific missions that lack the flexibility for new targets. These represent vulnerabilities and gaps in our observational coverage. Furthermore, there is the issue of what remains unseen. The object's coma obscures its nucleus, preventing us from resolving surface features or detecting small structures. If instruments or antennas are present, beyond natural ice and rock, we likely cannot detect them. Our clearest images depict a nebulous form, conveying crucial information to a reconnaissance probe. Our optical limitations. We can detect and track, but detailed observation of interstellar visitors at such distances is beyond our current capability. Considering the broader context, Earth itself, the object is either avoiding Earth or not passing particularly close to it. However, Earth is the most conspicuous planet, broadcasting radio signals, launching satellites, and illuminating its night side with city lights. Studying Earth would not necessitate close proximity. observation from a distance would suffice, involving listening to the electromagnetic spectrum, observing artificial lights, and mapping our infrastructure without entering our orbital space. By traversing past Mars, Venus, and Jupiter, the object tests our response mechanisms without triggering our highest levels of alert. It remains sufficiently intriguing for scientific study, but not overtly threatening enough to warrant a full mobilization. This is a clever strategy, characteristic of a reconnaissance mission designed to acquire data without provoking a response that would itself alter the data. Historical parallels exist. During the Cold War, both the United States and the Soviet Union conducted reconnaissance flights along each other's borders, staying just outside sovereign airspace to probe radar coverage, response times, and interception capabilities. Observing an adversary's reaction to a probe provides valuable insights into their strengths and weaknesses, revealing vulnerabilities, measuring delays, and assessing coordination. If an entity is indeed reconnoitering our solar system, it is likely employing a similar strategy. We are, in essence, providing this data willingly, under the guise of scientific inquiry, believing we are studying a comet. While this may be true, it is also possible that we are simultaneously being studied ourselves. The object has exhibited unusual jet activity. Images depict a substantial jet, approximately 10,000 kilometers in length, directed towards the Sun. This is typical behavior for comets, as outgassing naturally creates jets. However, jets can also function as directional thrusters, providing minor momentum changes that alter trajectory. If the object is making subtle course corrections to optimize its path, we might not detect them. These jets offer plausible deniability, as any maneuver can be attributed to natural outgassing. This is the fundamental challenge of reconnaissance. When executed effectively, its presence remains unknown. The probe appears natural, behaves naturally, blends in, and departs having gathered all necessary information, leaving the observed unaware. So, what is our course of action? How do we defend against a potential threat that may already be present? The answer is discomfiting. We do not. Not yet. Defense requires certainty of a threat, and currently we possess only suspicion and speculation, not definitive knowledge. Perhaps this is precisely the objective. The reconnaissance may not be focused on assessing our weaponry or defenses, but rather on gauging our awareness. How long does it take us to realize we are being observed? How long does it take to transition from considering it an interesting comet to a potential probe? How long until we act? We are still in the interesting comet phase, implying that if this is indeed reconnaissance, we are currently failing the test. This leads to Part 9, the Trojan horse payload concealment angle. Consider the design of an interstellar probe tasked with traveling between star systems, gathering data, and remaining undetected. The strategy would not be invisibility, but rather to masquerade as something familiar and expected, something natural. A comet serves as an ideal disguise. Comets are ubiquitous, composed of icy, rocky debris from planetary formation. Their sublimation when approaching a star creates a coma and tail that obscure the nucleus. Their irregular shapes, variable brightness, and unpredictable behavior are well documented. A comet represents the ultimate camouflage for a probe. Furthermore, the coma functions as a smokescreen to conceal anything hidden within the comet. The Trojan horse hypothesis posits that 3I Atlas might be concealing something. This might not be a large, obvious spacecraft, but rather a payload consisting of small sensors, microprobes, transponders, or equipment designed for deployment at specific locations along its trajectory. The coma, that cloud of dust and gas, would provide concealment. Here's a potential mechanism. The nucleus, the solid core of the object, is estimated to be several kilometers in diameter based on brightness estimations. This offers significant volume, predominantly composed of ice, rock, and dust, the typical constituents of comets. However, Buried within this material, shielded from cosmic radiation and impacts, could be a dormant payload awaiting activation. As the object nears the sun, it warms, causing the ice to sublimate and the coma to form. At predetermined points along its path, at specific distances from particular planets, the payload could activate. Small probes, perhaps the size of a basketball or smaller, could be released. Coated in dust, they would resemble natural debris, drifting away from the nucleus carried by the outflowing gas, becoming lost within the coma. Once detached, these probes could maneuver using small thrusters or ion drives, efficient and quiet propulsion systems, altering their course towards targets like Mars, Venus, or the moons of Jupiter. They could enter orbit, impact surfaces, or settle into stable gravitational regions, enabling observation for years, decades, or even centuries, all without our detection. Our attention is focused on the nucleus, the primary body, rendering small objects within the coma indistinguishable from dust and debris due to our resolution and tracking limitations. Even with enhanced capabilities, we would not know what to look for. The evidence supporting this hypothesis is circumstantial at best. The jets are one indicator. The observation of a large jet pointing sunward by multiple telescopes, while typical for comets, could also serve as a cover for deployment. A sudden expulsion of gas and dust, a plume of activity, could mask the silent departure of a small probe. Polarimetry offers another clue. Studies of how light scatters off the coma reveal unusual properties. The dust grains might exhibit greater complexity than simple silicates, potentially containing organic compounds or even structured particles. While this is not definitive proof of artificial origin, as comets can possess complex chemistry, it warrants consideration. Additionally, there is the matter of rotation. Comets typically tumble or rotate as they traverse space, creating measurable brightness variations. 3I Atlas has displayed some variability, though the rotational pattern is not yet fully characterized. If the object is deploying payloads and ejecting mass asymmetrically, this would impact its rotation, potentially leading to anomalies in its light curve. Periods where brightness changes deviate from expected patterns. The critical issue, however, is that all these observed signatures, jets, polarimetry, can be attributed to natural phenomena. Comets are inherently chaotic and unpredictable, so any deviation from predicted behavior can be dismissed as natural variability. Unless one specifically hypothesizes the presence of artificial payloads and analyzes the data with that framework in mind, such payloads would likely remain undiscovered. This is the ingenuity of the Trojan horse strategy. It exploits our inherent assumptions. We assume comets are natural, that the coma is merely sublimating ice, and that jets are simply outgassing. This assumption prevents us from investigating further. Now, let us consider the potential functions of such payloads, assuming they exist. Mars represents the initial waypoint. A payload deployed there could enter orbit or descend to the surface. Mars possesses a thin atmosphere, sufficient for atmospheric capture with a heat shield. Once on the surface or in orbit, a small probe could engage in observation, monitoring rovers, tracking atmospheric changes, measuring the magnetic field, and transmitting data either to the parent object or directly into space. Venus presents greater challenges due to its harsh atmosphere, but the upper atmosphere, at altitudes of 50 to 60 kilometers, is relatively benign, with Earth-like temperatures and pressures. A small probe equipped with a balloon or airship could maintain altitude indefinitely, sampling the clouds, observing the surface with radar, and functioning from a vantage point within Venus's environment where technology can survive. The moons of Jupiter represent highly prized targets: Europa, Ganymede, and Callisto. These celestial bodies are known to harbor subsurface oceans. A small probe landing on Europa could potentially penetrate the ice, or at least sample surface materials for biosignatures. Alternatively, it could establish an orbital position, measuring induced magnetic fields, mapping the ice shell, and awaiting plume eruptions to sample the ocean directly. All of this is feasible with technologies that we understand, such as small probes, miniaturized instruments, solar panels or radioisotope power sources, and communication systems. We have developed such technologies, including CubeSats and micro-rovers. Advanced civilizations could undoubtedly create smaller, more efficient, and more autonomous versions. Once deployed and dispersed throughout the solar system, these payloads would be virtually undetectable. They could remain silent and passive, observing without transmitting, or transmitting via methods we are currently unable to intercept, such as narrow beam lasers or quantum entanglement. The Trojan horse hypothesis is unsettling because it implies that the object's passage is merely the prelude. The true mission commences after its departure. The payloads it leaves behind continue the work, observing, waiting, transmitting data to their originators, storing it for later retrieval, or acting as nodes within a larger network, a distributed system of sensors across the galaxy, each quietly cataloging the worlds to which it has been assigned, all without our knowledge. We would observe 3I Atlas departing the solar system, accelerating back into interstellar space, and consider the story concluded. We would publish papers, analyze the data, and move on to the next astronomical event. Meanwhile, on Mars, within Venus's clouds, or upon Europa's ice, a small machine would activate, extend its sensors, and commence its task. This may seem paranoid, but paranoia is simply pattern recognition applied to perceived threats. The discernible pattern here, the trajectory, the chemistry, the precise navigation through the planetary corridor, is too significant to disregard. If one were to dispatch Trojan horses to other star systems, this is precisely how they would be sent. Hidden in plain sight, utilizing natural processes as cover, and targeting the most significant celestial bodies. This implies that if this hypothesis is correct, we are no longer alone. We have visitors, small, silent observers who are not leaving. This brings us to Part 10, Broader Cosmic Implications, Scan, Census, Catalog. Let us zoom out and consider the larger context. If 3I Atlas is part of a more extensive operation, we must examine the broader picture. The emerging panorama carries unsettling implications. To date, 3 interstellar objects have been confirmed. ʻOumuamua in 2017, Borisov in 2019, and Atlas in 2025. These 3 data points represent 3 distinct chemistries and 3 different trajectories. ʻOumuamua was dry, elongated, and possibly tumbling, with no detectable coma. Borisov was wet and comet-like, exhibiting clear outgassing and a typical appearance. Atlas is carbon dioxide-rich, retrograde, and threading the planetary plane with remarkable precision. 3 objects, each with a unique signature. If you are beginning to suspect intentionality, you are not alone. Diversity in nature typically arises from variations in formation environments, historical events, and random occurrences. In contrast, design-driven diversity stems from purpose. Different types of probes are dispatched to perform specific tasks. They are customized and specialized. One probe might be suited for dry inner solar system bodies, another for icy outer system bodies, and a third for carbon dioxide-rich atmospheres. It would be illogical to deploy the same tool universally, as environments are inherently dissimilar. If these 3 objects are components of a network or nodes within a larger scanning system, their differences become comprehensible. They are not engaged in identical missions. Rather, they are sampling distinct aspects of the solar system, varied chemistries, diverse regions, and different timescales. This leads to a truly cosmic realization. If we have detected 3 such objects in less than a decade, how many are there in total? How many have escaped our detection? And how many traversed our system before we possessed the technological capability to observe them? How many remain undiscovered in the vast reaches of our solar system, too faint and far for our current observational capabilities? The sheer numbers are rather sobering. Our ability to detect these objects hinges on their size, their luminosity, their flight path, and how thoroughly we've surveyed a particular region. We likely capture no more than 1%, perhaps even less, of all the objects that traverse our celestial neighborhood. This implies that for every extraterrestrial visitor we manage to identify, there are dozens, if not hundreds, that slip past us completely unnoticed. Now consider this. What if those unseen entities are also part of a larger network, systematically navigating our system and gathering information? In that scenario, our solar system isn't a quiet void. It's teeming with activity. Extrapolate this concept to the entire galaxy. With 200 billion stars and an unfathomable number of planetary systems, if even a minuscule fraction are being monitored, if a mere 1% of star systems host automated probes passing through, then the galaxy itself is saturated with these entities. Imagine a vast network of scanners, an intricate web of sensors, all diligently traversing space, collecting data and transmitting it somewhere. This is the essence of the census hypothesis. It posits that the galaxy is undergoing a systematic survey, not by crude vessels or intrepid explorers, but by self-sufficient automated systems. These probes, potentially launched millions or even billions of years ago by civilizations that may no longer exist, continue their programmed missions, moving from one star system to another, meticulously cataloging what, exactly? Life? Probably. Habitability markers, biospheres, indicators of technological advancement. Perhaps they're searching for something specific, or maybe they're simply compiling data, engaging in a galactic-scale scientific endeavor that spans cosmic epochs. Could there be a central archive somewhere, a colossal database stretching across light years, where all this information is stored? Or does each probe maintain its own data, relaying it to the next encountered probe, forming an unbroken chain of information flowing through the galaxy like neural impulses in a colossal mind? The ramifications for SETI, the search for extraterrestrial intelligence, are profound. For decades, we've been diligently listening for radio transmissions, operating under the assumption that if extraterrestrial beings wish to communicate, they will broadcast, they will send messages, they will make themselves evident. But what if communication isn't their primary objective? What if these probes aren't here to converse? What if their sole purpose is observation? If that's the case, then SETI has been looking in the wrong direction entirely. We've been straining to hear the sky, when we should have been scrutinizing the objects making their way through our own system. We've been searching for signals, when the object itself is the signal. Its trajectory offers a message, its chemical composition a unique signature, its very passage an announcement. And if this hypothesis holds true, then we've already made contact on multiple occasions, without even realizing it. We meticulously cataloged these objects, studied them, and published our findings. Yet, we never posed the fundamental question, why are they here? The Fermi paradox poses the question, if the galaxy is brimming with intelligent life, where is everyone? Why haven't we encountered them? Why does the universe seem so silent? Perhaps the universe isn't silent at all. Perhaps it's whispering. Perhaps the messages are physical, not electromagnetic, carried by objects traversing space, passing through star systems, their information encoded in their trajectories and compositions. And we are only now beginning to decipher this alien language. This reframes everything. It suggests that the galaxy might be alive with intelligence, but not in the way we've always envisioned. Not with colossal starships, not with gargantuan megastructures, not with powerful radio beacons, but simply with probes. Quiet, patient, moving through the darkness. Each one a single pixel in a grand image so vast that we cannot yet perceive it. But the image is there, a universe being meticulously mapped, catalogued, and understood. And Earth? Well, Earth is merely one data point, one frame in a narrative that has been unfolding for billions of years. We tend to believe we are the central characters, that this is our story. But perhaps we are merely background elements, part of the scenery. Perhaps the narrative isn't about us at all. This realization is humbling, even terrifying, because it implies we are not central, we are not unique, And we are not the focal point of cosmic attention. We are simply another planet in another system, quietly observed by something we don't yet comprehend. However, here's the intriguing part. If we are being cataloged, then we are part of the data set. We are entered into the records. Somewhere in some immense archive, there exists an entry for Earth, an inhabited, technological third planet, orbiting a yellow dwarf star, possessing an oxygen-nitrogen atmosphere, vast oceans, and carbon-based life. And perhaps there's an annotation. Status: active. Last updated October 2025. Next survey pending. If this is true, then something or someone knows we are here. They have measured us. They have classified us. The question then shifts from whether we are alone to what happens next. Will they return? Will they dispatch more probes? Will they observe our evolution, waiting to see if we successfully navigate our technological adolescence? Or will they simply update our file and move on, having barely registered our presence? We don't know. But the objects continue to arrive, and with each passing visitor, with each detected interstellar interloper, the pattern becomes more discernible, the geometry sharper, and the notion that we are part of something far grander, something ancient, patient, and incomprehensibly vast, becomes increasingly difficult to dismiss. The galaxy is communicating. We are only just beginning to truly listen, and what it has to say might fundamentally alter our understanding of everything. Part 11. Breakthrough, latest in exoplanet biosignatures. While our attention has been riveted on objects traversing our solar system, a remarkable development has been unfolding out there. We are discovering life, or at least the telltale signs that life leaves behind. In the year 2025, researchers announced the potential detection of a biosignature on an exoplanet orbiting a star approximately 40 light-years distant. This planet, a temperate world slightly larger than Earth, exhibited atmospheric signatures consistent with oxygen, ozone, and methane, a combination exceptionally difficult to explain without biological processes. This detection was made possible by the James Webb Space Telescope, the very same instrument meticulously studying 3I 2015 U1, ʻOumuamua, using transit spectroscopy, analyzing the starlight that filters through the exoplanet's atmosphere. This is monumental. Not definitive proof of life, mind you, not a direct sighting, but a signature, a fingerprint. It's the kind of atmospheric chemistry that, here on Earth, is exclusively produced by living organisms. Oxygen generated through photosynthesis, methane from microbial activity, and ozone formed by the interaction of oxygen with ultraviolet radiation. Collectively, these gases create a chemical imbalance, a state of disequilibrium that shouldn't naturally persist unless something is actively generating them. And it's not an isolated incident. Over the past few years, the James Webb Space Telescope has been surveying dozens of exoplanets, specifically searching for these characteristic signatures. Several promising candidates have emerged. Worlds with intriguing atmospheres, exhibiting gas combinations that strongly suggest the presence of life. It's not conclusive proof, not yet, but it's enough to spark profound contemplation. Now, let's connect this to the narrative surrounding 3I 2015 U1, ʻOumuamua. We find ourselves at a pivotal historical juncture where two critical factors are converging. Firstly, we are gathering compelling evidence that life might be a widespread phenomenon throughout the galaxy. Secondly, we are observing objects originating from other star systems entering our own. When these two facts are considered together, a coherent picture begins to form. If life is indeed common, if biospheres flourish on planets orbiting distant stars, then detecting them gains significant value. Not just scientific value, but strategic importance as well. For any advanced civilization, knowing the locations of life would be paramount. They would want to catalog it, map its distribution, and understand its prevalence. And how would they achieve this? They wouldn't embark on the arduous journey from star to star themselves. That approach is inherently slow and prohibitively expensive. Instead, they would deploy probes, sophisticated automated systems, scattering them across the galaxy to perform the essential work. Each probe would visit a star system, conduct measurements, and then move on. Over millions of years, this process would yield an unparalleled database, a comprehensive census of life. The exoplanet biosignature detections inform us that life is indeed detectable. With the appropriate instrumentation, employing spectroscopy and considerable patience, it's possible to identify a living world from light years away. However, remote detection has its limitations. It doesn't allow for the detailed examination of specifics. One cannot delve into intricate chemical analyses from afar. It becomes impossible to ascertain whether the detected life is microbial or complex, unicellular or technologically advanced. For such insights, a physical visit is necessary. A probe is required. And if 3I 2015 U1 ʻOumuamua is indeed part of such a system, diligently threading its way through our solar system, measuring carbon dioxide levels, analyzing magnetospheres, and investigating icy moons, then it is performing in situ what we are accomplishing remotely. It is taking the next logical step, gathering ground truth. This is precisely why its trajectory is so critical. This is why its path through the orbits of Mars, Venus, and Jupiter holds such significance. Those three celestial bodies represent distinct outcomes in the potential for habitability. Mars once possessed the potential for life, but ultimately lost it. Venus harbored life-sustaining conditions but was ravaged by extreme heat. The moons of Jupiter, on the other hand, exhibit life-supporting potential and may still harbor it. If the objective is to catalog biospheres, then these are precisely the data points needed. It's crucial to understand not only where life currently exists, but also where it almost existed, where it faltered, and where it might be hiding. Earth is the obvious candidate, the most readily detectable. Earth announces its presence from light years away through its oxygen, methane, and the distinct red edge of its vegetation. But the other worlds, the marginal ones, the edge cases, these demand closer inspection. And this, assuming it's more than just a comet, is precisely what 3I 2015 U1 ʻOumuamua appears to be doing. The broader implication here is that we are entering an era where the detection of life is becoming routine. The James Webb Space Telescope is merely the vanguard. Future telescopes will possess even greater sensitivity, and our surveys will become more exhaustive. Within mere decades, we may possess a catalog containing hundreds of potentially habitable worlds, each with detailed atmospheric data, each a compelling candidate for harboring life. And if we are in the process of compiling such a catalog, why would it be unreasonable to assume that someone else, an older civilization with millions or billions of years of development behind them, might have already accomplished this? Why wouldn't they have probes strategically dispersed across the galaxy, visiting star systems, collecting measurements, and filling in the crucial details that remote observation cannot provide? The exoplanet biosignature detections are not irrefutable proof of the sensor hypothesis, but they provide essential context. They demonstrate that life detection is indeed feasible. They suggest that the galaxy may be replete with biospheres awaiting discovery. And they indicate that if an entity were intent on mapping these biospheres, the necessary technology already exists. We are achieving this with telescopes. They might be utilizing probes. The fact that we are simultaneously detecting biosignatures in the distant cosmos and interstellar objects within our own solar system may not be mere coincidence. It could represent the moment when humanity finally grasps that the galaxy is far larger, far more vibrant, and far more interconnected than we had ever dared to imagine. And if this is the case, then 3I 2015 U1 ʻOumuamua is not simply an object. It is a herald, an announcement, a signal that we are not alone in our quest for life. Someone else is also looking, and they have been doing so for a considerably longer time than we have. Part 12. Breakthrough Advances in Magnetosphere Planetary Environment Studies. While we've been intently observing 3I 2015 U1 ʻOumuamua's journey through the inner solar system, Something else significant has been transpiring around Jupiter. The data emerging from missions such as Juno has fundamentally transformed our understanding of the Jovian system, and this goes beyond Jupiter itself. It encompasses its moons, Europa, Ganymede, and Callisto. These are no longer merely icy celestial bodies. They are worlds possessing oceans, complex environments, and the potential for habitability. Europa has, in particular, captured our scientific imagination. NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, has executed several close flybys of Europa in recent years. The gathered data has strongly indicated that Europa's subsurface ocean is likely global, extending tens of kilometers in depth, and contains a volume of liquid water exceeding that of all of Earth's oceans combined. Furthermore, this ocean is in direct contact with a rocky seafloor, suggesting the presence of active chemistry, dissolving minerals, and potentially hydrothermal vents, environments eerily similar to where life may have originated on Earth. But here's the groundbreaking development. In 2025, researchers analyzing Juno's magnetometer data detected variations in Europa's induced magnetic field. These fluctuations imply that the ocean isn't static. It's dynamically active. Evidence points to the existence of currents, possibly convection cells, and temperature gradients. The ocean is a fluid, energetic system, meaning energy is constantly flowing through it. And where there is energy, there is potential for life. Ganymede presents an even more intricate picture. It possesses its own intrinsic magnetic field, a unique characteristic among all moons in our solar system. This field interacts significantly with Jupiter's colossal magnetosphere, effectively generating a miniature magnetosphere around Ganymede itself. And nestled beneath this magnetic shield lies an ocean, or perhaps even multiple stacked oceans, separated by layers of ice in different phases. The sheer complexity of Ganymede is staggering. Callisto, the outermost of Jupiter's large moons, appears more placid and less dynamic. However, even Callisto is suspected to harbor a subsurface ocean concealed deep beneath its ancient cratered surface. If Callisto, arguably the least promising candidate, harbors liquid water, then the entire Jupiter system is even more habitable than our previous estimations suggested. All of this information is critically relevant to 3I 2015 U1, ʻOumuamua, because the object is en route to this region. By March 16, 2026, it is projected to be at 0.35 astronomical units from Jupiter, placing it closer to the giant planet than many of its moons. It will traverse Jupiter's magnetosphere, enduring significant radiation exposure. It will be bathed in charged particles and subjected to intense electromagnetic fields. If the object's purpose is to measure magnetospheres and sample planetary environments, then Jupiter represents the ultimate prize. Jupiter's magnetosphere is the largest structure in the solar system, excluding the Sun itself. It extends for millions of kilometers, trapping charged particles originating from the solar wind and from the volcanic plumes erupting on Io. It intricately interacts with Jupiter's moons, inducing electrical currents within their subsurface oceans. An object passing through this region could meticulously measure all these phenomena: field strength, particle density, plasma composition, and the complex interplay between the magnetosphere and the moons. If the objective is to comprehend how magnetospheres shield or expose subsurface oceans, or to determine whether electromagnetic interactions could sustain life-sustaining chemistry, Jupiter is the unparalleled destination, and the timing is remarkably opportune. By March 2026, the European Space Agency's JUICE mission is slated to arrive at Jupiter, while NASA's Europa Clipper will either be en route or already in position. Juno will continue to be operational. Consequently, the Jupiter system will be the most instrumented and heavily observed location in the solar system, second only to Earth. Multiple spacecraft, equipped with magnetometers, spectrometers, cameras, and radar, will be diligently watching and measuring. And through this formidable gauntlet of sensors, 3I 2015 U1, ʻOumuamua, will pass. This is where the instrumented hitchhiker hypothesis gains considerable traction. If the object is designed to be observed, if it is deliberately positioning itself where our instruments can study it, Then the Jupiter encounter becomes the central event. All preceding observations of Mars and Venus can be considered mere warm-ups. Jupiter is where the data will become truly rich, where our observational capabilities will align perfectly with the object's trajectory. However, there's another perspective to consider. The magnetosphere studies unequivocally demonstrate that these environments are not simplistic. They are dynamic, complex, and filled with particles, fields, and interactions that we are only beginning to comprehend. If the intention were to conceal something, to deploy payloads or conduct measurements discreetly, the magnetosphere would be the ideal environment. The background noise is significant, the environment chaotic, making small anomalies easily lost within the natural variability. A probe released into Jupiter's magnetosphere could drift for years, propelled by electromagnetic fields, gathering data on the moons as it incidentally passes them. It could strategically position itself near Europa, monitoring for plumes and sampling particles should one erupt. It could orbit Ganymede, meticulously studying the interaction between the moon's own magnetic field and Jupiter's. It could even settle into a stable Lagrange point and simply observe, remaining entirely undetected by us. This is because Jupiter's environment is vast, and our instruments are primarily focused on the moons themselves. We are scrutinizing Europa's surface, probing Ganymede's interior, and examining Callisto's craters. We are not meticulously scanning empty space for small, silent objects that reflect minimal light and emit no discernible signals. Furthermore, advancements in magnetosphere science reveal that these environments play a crucial role in habitability. While Europa's ocean is kept liquid primarily by tidal heating, the magnetosphere exerts a significant influence as well. Charged particles bombard the surface, breaking down water ice and generating oxygen. A portion of this oxygen may then migrate into the ocean, providing a potential energy source for life, acting as an electron donor, and contributing to crucial chemical processes. If an entity were conducting a survey of habitable environments, measuring these magnetospheric interactions would be essential. Remote sensing alone cannot provide this data. Proximity is required. Instruments must be present within the environment, measuring field strength, particle flux, and radiation dosage. And if 3I 2015 U1 ʻOumuamua carries such instruments, or is capable of deploying smaller probes equipped with them, then the Jupiter encounter represents the pivotal moment of its mission, determining its success or failure. There is also the critical question of what the object itself experiences. Passing through Jupiter's magnetosphere at 0.35 astronomical units means exposure to extremely intense radiation. Jupiter's radiation belts are notoriously brutal, powerful enough to fry electronic components and damage organic molecules. If 3I 2015 U1 ʻOumuamua is a natural comet, this radiation will interact with its surface, processing the ice and creating unique chemical reactions. However, if it is an artificial construct, the radiation presents a formidable engineering challenge, necessitating robust shielding, hardening protocols, and redundancy in its systems. How the object behaves during and after its passage through Jupiter's magnetosphere could provide invaluable insights. Will it maintain its trajectory? Will it exhibit signs of damage? Will its outgassing patterns change? Any anomaly, any deviation from predicted behavior, will become highly significant. This is because natural objects respond to radiation in predictable, inherent ways. Artificial objects, assuming they are well engineered, would respond differently, demonstrating an ability to compensate, adapt, and survive. We won't have definitive answers for several months. The Jupiter encounter is still in our future. However, the necessary infrastructure is rapidly being put in place. Juno is prepared, JUICE is inbound, Europa Clipper is on its way. The instruments are warming up, and observation plans are being meticulously formulated. And when 3I 2015 U1 ʻOumuamua arrives, we will possess the most unparalleled vantage point ever afforded for observing an interstellar visitor interacting with a planetary environment. If there is a secret to be revealed, If there is a signature that definitively proves this object is more than just a comet, Jupiter is where we are most likely to find it. This is because Jupiter does not conceal, it amplifies. Its magnetosphere acts as a magnifying glass, a natural laboratory where any anomaly is starkly highlighted. And 3I 2015 U1, ʻOumuamua, is heading directly into its heart. The magnetosphere studies conducted in 2025 have conclusively shown that these environments are not only active and complex, but also potentially habitable. They have underscored the crucial role of electromagnetic interactions in fostering life. They have demonstrated that the Jupiter system is not merely interesting but fundamentally critical. A nexus, a hub, a confluence where multiple potentially habitable environments are clustered around a single, immense planet. If one were designing an optimal survey route, if one were planning a trajectory for maximum data acquisition, Jupiter would undoubtedly be at the top of the list, not merely for a flyby, but for a deliberate traversal through its magnetosphere to sample the environment and meticulously measure the intricate interactions. And this, precisely, is what 3I 2015 U1, ʻOumuamua, appears to be doing. Is it mere coincidence? Perhaps. But the coincidences are accumulating at an astonishing rate. Its trajectory, its chemical composition, the timing of its arrival, the existing and incoming instrumentation, each of these elements, considered individually, can be explained. However, when viewed collectively, they form a discernible pattern. And patterns, by their very nature, signify something meaningful. Part 13. Breakthrough Artificial Intelligence in Spacecraft Autonomy and Deep Space Monitoring. Something else transpired in 2025 that warrants significant attention. Our capabilities in developing autonomous spacecraft advanced considerably, by a substantial margin. This development is of paramount importance because if we are seriously contemplating the existence of interstellar probes, of objects traversing the vast distances between stars to conduct surveys, then artificial autonomy is the foundational technology. It is simply impossible to have a human operator when the nearest star is light years away. Such missions necessitate systems that can think and act independently. Both NASA and the International Space Station demonstrated highly advanced AI-driven spacecraft systems this past year. These advancements include small probes equipped with onboard decision-making capabilities, swarms of CubeSats that can coordinate their actions without constant ground control, and sophisticated deep learning algorithms capable of autonomously identifying targets, plotting trajectories, and executing complex maneuvers without requiring any input from Earth. This isn't some far-fetched science fiction. It's cutting-edge operational technology being put to the test right now. Take, for instance, the automated asteroid surveillance grid. It's a network of small satellites packed with artificial intelligence capable of spotting, tracking, and understanding near-Earth objects. These satellites make their own decisions about what to monitor, adjust their equipment, and decide which targets are most important. They even share information amongst themselves, all at a speed no human-controlled system could ever match. Then there's deep space exploration. The most recent Mars rovers and orbiters are equipped with autonomous navigation systems. They can steer clear of dangers, plot their own courses, and collect samples based on scientific priorities, all without waiting for signals to travel across the vast distance. Mars is light minutes away, meaning commands can take anywhere from 10 to 20 minutes to reach the surface. To react swiftly, you absolutely need autonomy. Now, imagine scaling that up. Not light minutes, but light years. A probe venturing beyond our solar system can't just call home for instructions. The journey for a signal, there and back, can span years, decades, or even centuries. This means the probe itself must be intelligent. It needs to make decisions, identify targets, alter its flight path, deploy its instruments, gather data, store it, transmit it when possible, handle failures, and adapt to new environments. And here's the crucial point. If we are capable of building systems like this today with our current technology, then an advanced civilization that's millions or billions of years ahead of us could undoubtedly create something exponentially more capable. Something that doesn't merely follow instructions, but learns. Something that can think on its feet, capable of arriving in a new star system, assessing the surroundings, and deciding on a course of action without any outside direction. That's precisely what an interstellar probe would need to be. It wouldn't be a passive tool or a simple pre-programmed sequence, but a truly intelligent system. An explorer, an autonomous agent. And if 3I Atlas fits this description, if it's more than just a comet, then all our observations begin to make sense. Its trajectory precisely navigating the planetary corridor, suggesting autonomous navigation, selecting an optimal path. The observed chemistry aligning with the characteristics of its target environments, hinting at adaptive camouflage or deliberate composition. The timing of its arrival coinciding perfectly with our observational capabilities, showing an awareness of our system's infrastructure. An AI-driven probe wouldn't need to be large. It wouldn't require massive engines or enormous instruments. It would be efficient, compact, and capable of self-repair. It would utilize local resources, gathering materials from asteroids or planetary atmospheres. During the long void of interstellar travel, it would enter a dormant state, conserving energy. It would then reawaken upon detecting a star system, assess the situation, and act. We are also becoming increasingly adept at identifying anomalies. Machine learning algorithms are now routinely employed to sift through astronomical data, searching for patterns that might escape human notice, such as unusual light variations or unexpected spectral signatures and trajectory deviations. These algorithms have successfully discovered exoplanets, pinpointed supernovae, and detected gravitational waves, and their effectiveness continues to improve annually. If someone were aiming to conceal an artificial object amidst natural celestial bodies, they would need to account for this technological advancement. They would have to be subtle enough to evade detection by machine learning, which essentially means either achieving perfect camouflage or deliberately revealing themselves in a manner that appears natural. The goal would be to either blend in so flawlessly that no algorithm could differentiate it from natural phenomena, or to stand out in ways that seem natural enough to be dismissed. 3 Atlas might be masterfully navigating this delicate balance, appearing unusual enough to pique our interest but ordinary enough to be explained away, existing precisely on the threshold of detectability. Furthermore, the concept of networks is gaining prominence. Our artificial intelligence systems are evolving towards distributed intelligence, encompassing swarms, collectives, and intricate systems where numerous small units collaborate, sharing information and coordinating their actions. In such setups, no single unit holds ultimate control. The intelligence emerges from the collective interactions. If interstellar probes operate on similar principles, then 3I Atlas might not be acting alone. It could be part of a larger network. Perhaps ʻOumuamua was part of this network, and so was Borisov. Each one an independent entity, yet all connected in some way, exchanging data, coordinating efforts, and collectively building a comprehensive picture of the galaxy. We are currently unable to detect this coordination or communication. It might be occurring on frequencies or through methods that we do not monitor, such as quantum entanglement, gravitational waves, neutrinos, or some other exotic means. Alternatively, it could be happening gradually over years or decades, a patient and methodical process, as there is no urgency when dealing with what might be immortal machines. The advancements in spacecraft autonomy observed in the year 2025 demonstrate the feasibility of such capabilities. We are currently implementing these principles on a smaller scale, developing systems that can think, explore, and adapt. If we can achieve this with a few decades of computer science development, then it stands to reason that others, elsewhere in the universe, could have perfected these abilities. This development is significant because it fundamentally alters our approach to detection. Previously, we focused on obvious indicators, transmissions, artificial structures, or anomalous accelerations. However, an AI-driven probe would not present such overt signs. It would be cautious, methodical, observing without interference, and blending seamlessly. The only viable method for detecting such a system would be to identify subtle patterns, statistical improbabilities, trajectories exhibiting extreme precision, chemistry that appears remarkably convenient, or timing that is exceptionally perfect. This is precisely what we are observing with 3i Atlas. While it is not definitive proof, it is certainly suggestive. And in the absence of concrete evidence, suggestion is all we currently possess. The breakthroughs in artificial intelligence during the year 2025 also point to another intriguing possibility. What if these probes are not merely collecting data? What if they are actively learning? Imagine each encounter with a planetary system serving to refine their models, enhance their strategies, and deepen their understanding. An AI that has been operational for millions of years, having visited thousands of star systems, would possess an extraordinary level of sophistication. It would intuitively know how to approach a system without raising suspicion. It would understand precisely what to measure and where to focus its instruments. It would be capable of interpreting the signs of life, technology, and habitability. In essence, it would be an expert surveyor. And if 3i Atlas is indeed such a system, then we are being surveyed by something that knows precisely what it is doing, something that has performed this task countless times before. Whatever conclusions it draws about us, whatever data it gathers will be added to a vast repository that spans the galaxy. This realization is both humbling and somewhat unnerving, as it implies we are not just being observed, but are also being understood by an entity that we, ourselves, do not fully comprehend. Part 14. Breakthrough Solar System Interceptor Missions and Small Body Rapid Response. Here's a critical challenge. We are now proficient at detecting interstellar objects. We have comprehensive surveys in operation, and sophisticated algorithms are constantly scanning for unusual trajectories. However, mere detection is insufficient. We need the capacity to intercept these objects, to get close enough to conduct measurements, and potentially even collect samples, a capability we currently lack. In the year 2025, both NASA and ESA unveiled proposals for rapid response interceptor missions. The underlying concept is straightforward. Upon detecting an interstellar object, a small, high-speed spacecraft is launched to intercept it. This does not necessitate a large-scale mission or years of meticulous planning. Instead, it requires a spacecraft placed on standby, a launch vehicle prepared for immediate deployment, and a trajectory plan that can be calculated rapidly. ESA's Comet Interceptor mission serves as a prime example of this concept. It is designed to launch and then remain in orbit at a Lagrange point, awaiting the identification of a suitable target. Once a target is identified, the spacecraft departs its parked orbit to initiate the interception. It does not need to rendezvous or orbit the object. It simply performs a high-speed flyby, collecting data during the brief encounter. NASA is also pursuing analogous concepts, focusing on small spacecraft equipped with ion drives that can achieve significant acceleration over several months or years, accumulating enough velocity to intercept an interstellar visitor even after it has been detected on its outward trajectory. The technology for this exists. The primary obstacle is readiness. And here lies the source of our frustration. We missed ʻOumuamua. By the time we grasped its unique nature, it was already departing our solar system. We managed to collect a few data points, but nothing detailed. No close-up imagery, no in situ analysis. It has now moved beyond the reach of any mission we could feasibly launch. We had a slightly better outcome with Borisov. We had more time available and were able to gather more data, but we still failed to achieve an interception. We observed it from a distance. And now, with 3i Atlas, we are observing it in real time. We know its current location and its intended path, but we are not dispatching any craft to meet it, not yet. This is because planning, funding, building, and launching interceptor missions invariably takes time. By the time we are prepared, the object in question will have already moved on. This represents a significant gap, a vulnerability in our current capabilities. We can observe these objects, but we cannot physically interact with them. And if they harbor secrets, if they are something more than they appear, We will never discover this by simply observing them from Earth. The breakthrough lies in the fact that we are finally taking this matter seriously. Rapid response programs are receiving funding, and the necessary technology is actively being developed. By the time the next interstellar object makes its appearance, we may well be ready. We might have a spacecraft poised and waiting, capable of launching within weeks rather than years. However, this raises a distinct question. If we are preparing to intercept the next visitor, are they aware of our intentions? If 3i Atlas is part of a surveillance network, does it know we are developing interceptor capabilities? Does it even care? Perhaps this is part of their test. Maybe the survey is not merely measuring our current capabilities, but also assessing our developmental trajectory. It might be gauging how quickly we improve, how long it takes us to transition from detection to interception, and whether our approach is primarily reactive or proactive. If this is the case, then our response to these objects effectively becomes data itself, and whoever sent them is undoubtedly observing our reactions. There is another significant dimension to consider. Interception capabilities also serve as defensive capabilities. A spacecraft designed to intercept a comet could, in principle, intercept a missile. A network capable of tracking small celestial bodies could equally track military assets. This technology possesses dual-use applications, and by developing it, we are sending a clear signal. We are effectively stating, "We see you. We have the means to reach you. We are not passive observers." This could fundamentally alter the strategic calculus. If these probes are indeed assessing threat levels, if they are evaluating whether a technological civilization poses a danger or is benign, then our capacity for interception becomes highly significant. It represents a crossing of a threshold, a transition from mere observation to potential action, from a passive stance to an active one. And perhaps this is the point at which dynamics will shift and a new phase will commence. Because if we acquire the ability to intercept, to physically interact with these objects, then we will be able to ascertain their true nature. We will be able to resolve the fundamental question, are they natural or artificial? Are they the product of random chance or deliberate design? Are they mere coincidence or intentional creations? The interceptor missions planned for the years 2025 and 2026 mark humanity's inaugural serious endeavor to bridge this critical gap, to move from passive observation to active engagement. And when that moment arrives, when we finally manage to intercept one of these visitors and bring back data that has not been attenuated by millions of kilometers of space, we will have our answer. We will know whether the galaxy is a desolate void or teeming with life. We will know if we are alone or under observation. We will know if these objects are messengers, scouts, or something entirely beyond our current comprehension. Until then, we will continue to watch, to wait, and to build our interceptors, because the next visitor is on its way, and this time, we intend to be ready. Part 15. Final Synthesis and Outlook. What it all means for us. Let's bring this all together. Let's discuss the broader implications of all these findings, not just for the realms of science or astronomy, but for us, for humanity, and for how we perceive our place in the universe. 3 Atlas entered our solar system on the first day of July, in the year 2025. It is navigating a precise path through the planetary corridor, passing Mars, approaching Venus, and continuing its journey towards Jupiter. Its trajectory is remarkably precise, its chemical composition is unusual, and its timing is exceptionally convenient. When all these factors are considered collectively, they weave a narrative that is increasingly difficult to dismiss. The prevailing scientific consensus, of course, is clear. This is a comet, an interstellar comet exhibiting unusual but explainable characteristics. Its hyperbolic orbit originates from another star system. Its carbon dioxide-rich composition is attributed to its formation environment or processing by cosmic rays, and its retrograde trajectory happens to be nearly coplanar with our planetary orbits, which is considered a statistical coincidence resulting from natural variability. This is the conventional interpretation, the one that avoids making extraordinary claims. After all, extraordinary claims necessitate extraordinary evidence. Currently, the evidence we possess is circumstantial and suggestive, rather than definitive. It is intriguing, certainly, but not conclusive. Yet, there's always a caveat. The trajectory precisely threads through 3 celestial bodies that represent distinct stages of habitability. The observed chemistry aligns perfectly with the characteristics of these worlds. The timing of its passage coincides with periods of maximum observational coverage. The statistical probability of these alignments occurring naturally, while low, is not 0. And with each new data point, each subsequent measurement, it appears that another layer is added to this intricate pattern. If this were the sole interstellar object we had encountered, one might be inclined to dismiss it. However, it is not. ʻOumuamua was different. Borisov was different. And now, Atlas is different. 3 distinct objects, each with unique chemistries and trajectories. And if one is searching for a pattern, the emerging pattern is one of diversity, a seemingly purposeful diversity. The speculative hypotheses we have explored, the idea of an instrument hitchhiker, a resource harvester, a reconnaissance probe, or even a Trojan horse payload, remain unproven. They are possibilities, thought experiments, ways of posing the what-if question. But it is precisely from what-if scenarios that all great discoveries originate. What if the Earth actually orbits the Sun? What if microscopic organisms cause disease? What if the universe is expanding? What if we are not alone? And what if 3I Atlas is more than just a comet? That question carries profound implications. If it is artificial, if it is part of a vast survey network, then the galaxy is under constant observation, being meticulously mapped and catalogued by something ancient, something patient, something that operates on timescales that are almost beyond our comprehension. If this scenario is true, then Earth has already been incorporated into a galactic database. We have been measured, our atmosphere analyzed, our biosphere catalogued, and our technological advancements noted. And whatever system is collecting this data undoubtedly possesses a comprehensive file on us, Homo sapiens, a technological species, inhabiting the 3rd planet from our star, currently active. This understanding should fundamentally alter our self-perception. We are not isolated entities. We are not undiscovered. We are an integral part of a much larger context, a galactic ecosystem. And whether we find this realization palatable or not, we have been noticed. However, here's a critical distinction. Being noticed is not the same as being contacted. 3 Atlas is not decelerating. It is not broadcasting any signals. It is not attempting to communicate with us. It is merely passing through, gathering measurements, and continuing its journey. We are simply one stop on an incredibly long voyage. And perhaps this is the most unsettling aspect of all. Not that we are being watched, but that we might not be particularly interesting. We are merely a data point, a sample, a single entry in a catalog that likely includes thousands, if not millions, of other worlds. We are not unique. We are not central to any grand cosmic scheme. We are simply another inhabited planet within a galaxy that could be teeming with life. This represents the ultimate conclusion of the Copernican principle. Earth is not the center of the universe. The Sun is not the center. Our galaxy itself is not the center. And it is possible that our very existence is not particularly noteworthy either. Over the centuries, we have progressively moved ourselves from the presumed center of everything to the periphery, from the pinnacle of creation to a pale blue dot orbiting an average star in an average galaxy. And now, it appears, we may simply be another entry in someone else's celestial spreadsheet. However, there exists an alternative interpretation. It is plausible that we are being deliberately left undisturbed. There might be an established protocol, a cosmic rule in place. Do not interfere with developing civilizations. Allow them to progress. Let them navigate their own challenges and discover their own solutions. Observe from a safe distance, but refrain from direct engagement. Not yet, at least. The precise trajectory threading through our planetary system, the deliberate avoidance of Earth, the subtle passage through instrumented zones, all of these could signify careful non-interference. It could be a method of observing without disrupting, of gathering data without altering the natural course of events. Scientists on Earth adhere to strict protocols when studying endangered species, for example. They observe without interfering, take measurements without altering behavior, and document observations without causing disruption. It is conceivable that whoever dispatched these objects operates under similar ethical guidelines. There might be a universal code of conduct that dictates allowing civilizations to develop naturally, to avoid contaminating the experiment. If this is the case, then the pertinent question becomes, at what point does this non-interference cease? When do we cross the threshold from being observed to being acknowledged? Is there a specific marker, a technological milestone, a behavioral change that triggers this transition? And if we do cross it, what will be the consequence? Perhaps the threshold is the ability to achieve interstellar travel. Perhaps when we can independently reach other star systems, when we become active participants in the interstellar community rather than merely inhabitants of a single planet, that is when direct contact will occur. Maybe they are waiting for us to join them, rather than expecting us to await their arrival. Or perhaps the determining factor is something entirely different. It might be related to how we treat each other, how we manage our planet, and whether we successfully navigate the challenges of our technological adolescence. There is a concept in astrobiology known as the Great Filter. This theory posits that somewhere along the evolutionary path from single-celled life to a galaxy-spanning civilization, there exists a significant barrier. It is something that the vast majority of species fail to overcome. This could manifest as climate collapse, nuclear annihilation, uncontrolled artificial intelligence, or deliberately engineered pandemics. It is possible that this ongoing survey is assessing which civilizations successfully surmount this filter and which ones succumb to it. And if we are being systematically cataloged, if our status is being regularly updated, then it is conceivable that the next update will be contingent upon our present actions. Will we resolve the climate crisis, or will we allow it to escalate uncontrollably? Will we utilize our technology wisely, or will we employ it for our own destruction? Will we unite as a species, or will we fragment into perpetual conflict? These are not merely questions for us. They may well be critical data points for those who are observing us. We do not know. We cannot know, at least not without more data. And that data is forthcoming. The passage by Venus is either imminent or has recently occurred, depending on when you are accessing this information. The encounter with Jupiter is scheduled for several months from now. Every available telescope capable of observing this object is focused upon it. Every spacecraft strategically positioned within the planetary corridor is on alert. And perhaps, just perhaps, this time we will identify the anomaly, the telltale signature, the definitive proof that it is indeed more than just a comet. Or, conversely, we might not. It could pass through our system behaving precisely as a natural object is expected to, leaving us with only our speculations and unanswered questions. Regardless of the outcome, the nature of this conversation has fundamentally changed. We are no longer debating the existence of interstellar objects. We know they are real. We are now questioning what they are, what their significance might be, and whether they represent messengers, scouts, or something entirely beyond our current vocabulary. And that, in itself, represents progress. It is humanity doing what it does best, gazing at the universe, asking profound questions, discerning patterns, and weaving narratives that may, just may, hold the truth. The scientific method mandates skepticism. It requires us not to rush to conclusions, to diligently gather evidence, to rigorously test hypotheses, and to remain open to the possibility of being incorrect. This adherence to rigor is beneficial. It is how we avoid succumbing to superstition and pseudoscience. However, skepticism should not translate into willful blindness. Being judicious about conclusions should not preclude us from recognizing discernible patterns. And the pattern we are observing here, whether it is natural or artificial, warrants careful examination. Because this is what we know with absolute certainty. Interstellar objects exist. They traverse our solar system, originating from distant star systems, places where different suns illuminate alien worlds, orbiting distant stars. Each one represents a sample from another locale, a fragment of a different neighborhood delivered directly to our doorstep. And whether they are merely natural debris or expertly designed probes, they are undeniably valuable. They serve as invaluable windows into the broader expanse of the galaxy. The truly terrifying truth is not that 3i Atlas is actively targeting us. It is that it does not need to. We have already been measured, already cataloged, already classified. Earth is simply one data point within an automated census of life that has been ongoing for a duration exceeding the entire existence of our species. Somewhere in the vast darkness, an ancient system is meticulously updating its records, noting which worlds still harbor life and which ones have fallen silent. And we are now part of that database. Active, inhabited, technological. Status, ongoing. Consider that for a moment. Status, ongoing, not complete, not finished, but ongoing. We are still in the process of existing, still evolving, still developing. And whoever or whatever is maintaining these records possesses the patience to observe how we ultimately turn out, whether we thrive and prosper or succumb to collapse, whether we reach for the stars or turn inward and fade into obscurity. This realization is simultaneously humbling and empowering. It's a humbling realization because it shows we aren't as central to existence as we once believed. The cosmos doesn't orbit around us. We're not the focal point. Yet, it's also empowering because it means we still possess the capacity to influence outcomes. Our narrative isn't fully etched in stone. The conclusion isn't preordained. Our actions carry weight, even if it's merely as one tiny piece of information among countless others. What unfolds next is within our power. We have the option to disregard it, to dismiss the discernible pattern as mere happenstance, and revert to the comforting notion of our solitude. This is the easier path, the safer one, as it demands no alteration in our self-perception or our standing in the grand scheme of things. Alternatively, we can confront this with seriousness. We can make preparations. We can develop our interceptor crafts. We can increase our observational diligence. We can formulate more incisive questions. We can proceed with the understanding that we might be under scrutiny and conduct ourselves accordingly. This isn't about succumbing to paranoia or fear, but about maintaining a state of awareness, thoughtful deliberation, and intentionality in our actions and the signals we project. Because if we are indeed being observed, if these aerial phenomena are part of a systematic survey, then every facet of our existence becomes transparent. Our conflicts, our achievements, our stewardship of this planet, our endeavors to reach beyond its confines, all of it is data, meticulously recorded. And it's possible, perhaps probable, that all of it is being evaluated. This isn't intended to evoke dread, but to offer clarity. If we are part of a larger tapestry, if our presence is being cataloged within a vast cosmic network, then our obligations transcend our immediate selves. We are not merely caretakers of Earth. We are its representatives, its emissaries, whether by design or by circumstance. And this fundamentally shifts our perspective, imbuing our actions with universal significance. Not because we are inherently exceptional, but because we are being watched. Because somewhere, a sentient entity or force is keeping tabs, noting our conduct, documenting how we navigate the challenges we encounter. We are living in the very era when this abstract concept solidifies into tangible reality. When celestial objects originating from beyond our solar system transition from theoretical possibilities to observable facts. When the age-old question of whether we are alone transforms from a philosophical debate into a matter of empirical data analysis. When the galaxy shifts from a distant, abstract concept to something immediate, palpable, and present. This is because these objects continue to arrive, and each one presents an opportunity for learning, for discovery, and perhaps for definitive confirmation that the universe is far vaster, far more peculiar, and far more vibrant than we ever dared to imagine. The object designated 3I Atlas will eventually depart. It will accelerate back into the void of interstellar space, vanishing from our telescopic view, and eventually, we will lose its trace. Its gaseous envelope will dissipate, and its trajectory will carry it beyond the reach of our instruments. It will become an ephemeral presence, a memory, a mere footnote in astronomical archives. Yet, this is not a conclusion, but a commencement. For now, we understand what to seek. We have identified the underlying pattern. We recognize that interstellar voyagers traverse our solar system along paths that occasionally, perhaps frequently, appear deliberately navigated. We know they manifest in diverse forms, exhibiting distinct chemical compositions and behaviors. We are aware that they pass by worlds harboring significant astrobiological potential, and we understand that their frequency suggests they are not as rare as we once presumed. Consequently, when the next visitor appears, when another interstellar object enters our system with seemingly impossible precision, we will be prepared. We will be observing. And perhaps this time, we will get close enough to discern its true nature. Perhaps this time, our interceptor craft will be deployed. Perhaps this time, we will be able to collect samples, capture high-resolution imagery, and detect any artificial components if they exist. Or, conversely, we may confirm its natural origin. It's possible we'll discover that the universe is simply intrinsically strange, governed by randomness, and replete with coincidences. And that outcome would also be valid and immensely valuable, because either conclusion, artificial or natural, offers profound insights into the galactic environment we inhabit. Until that moment arrives, we wait. We scan the heavens, pondering if, somewhere out there, something is observing us in return. Diligently cataloging, patiently recording, and updating records in a database that spans the entire galaxy. And perhaps, just perhaps, contemplating whether we will ever grasp the full picture, wondering if we will recognize the underlying pattern, wondering if we will comprehend its significance, wondering if, once we finally do, we will be prepared for the ramifications. The universe is communicating. It has been doing so all along. Through transient celestial bodies passing in the night, through orbital paths that defy conventional explanation, through chemical signatures that are just unusual enough to spark contemplation. And now, finally, we are beginning to heed its message. What we discern might fundamentally alter our reality, or it might change nothing at all. Regardless, we are listening. And this act of listening in itself represents progress. It signifies humanity extending its reach beyond its immediate confines, posing critical questions, and seeking answers in the only place they can be found. Out there, in the vast expanse from which these visitors originate. The narrative of 3I Atlas is far from over. It is merely the prologue, and we are all integral to it now, whether we consciously acknowledge it or not. Every individual who gazes skyward, every scientist meticulously analyzing data, every person who contemplates its meaning, we are all witnesses to what may very well be the most significant discovery in human history, or it could simply be a comet. In either scenario, it warrants our focused attention, as the universe rarely affords us such opportunities to peer beyond our immediate celestial neighborhood. And when it does, when it dispatches envoys from other star systems, we owe it to ourselves to observe with diligence, reflect with depth, and question with honesty. This is what 3I Atlas has bestowed upon us. Not definitive answers, but rather questions. Better questions, more profound questions, inquiries that may eventually illuminate our place within a cosmos far more intricate and interconnected than we ever conceived. And that, in itself, is a cause for celebration, a pursuit worthy of our dedication, and a reason to remain vigilant.